Hello, good morning. So, well, I hope that you have good time, okay, this morning. And well, I assume that you already finished watching the video. So I will briefly, review again what I have covered in the video, okay? So, in the last video, I introduced you the optimality condition. The first one is a local optimum, right? And global optimum. Also, the condition for, we call it necessary condition and sufficient conditions. And the other things is positive definite and negative definite, right? So let us move through the way. I show you the definition of local optimum and global optimum, right? For example, from this one, from this graph, you see that, well, we have local maximum, okay? Or the point local maximum and some points, B1, B2, it's a local minimum. Right? A1, A2, A3 is a local maximum. And well, it is not necessary to be, well, the global optimum is, global maximum needs not to be local maximum. Okay, we can have, for example, this graph. No, which graph? Yeah, here you see that global maximum is here, right? But we have two local maximum. Okay, when we say local maximum, it's a maximum among, well, neighbor points. Okay, so for local minimum also we compare, well, it's minimum amongst the adjacent points, the neighbor around that area. This point is minimum, this point minimum. Okay, and you see that for global minimum, well, it can be global maximum or global minimum can be local minimum or local maximum. It depends. But it's not necessary. Okay, we can have, well, local maximum, which has very high value, right? Has the highest value, and then we call it, global maximum. Okay, and for the necessary condition, the first thing is if a function f(x) is defined in the interval a, b, right? From a, in the interval a, b, and have relative minimum at x star. Of course, x star must lie in A and B. And if the derivative exists as a finite number at x star, then the derivative, okay, f prime at x star must be 0. Okay. However, if we have a point where the f prime x star is 0, we cannot guarantee that that point is minimum or maximum. Okay, but what we say here is, well, if x star is inside our interested interval, and that x star is minimum or maximum, the derivative at that point must be exit and must be 0. Okay, if and then. Okay, so this theorem can be proved, if x star is a relative maximum. Also, minimum or maximum, you got, well, it's necessary to have f prime or derivative at that point 0. Okay, but the theorem doesn't say what happened if minimum or maximum occur at point x star where the derivative fail to exist. If that point, well, you cannot find the derivative, yeah, it doesn't cover by this condition, okay? And the theorem doesn't say what happens if a minimum or maximum occur at the end point, okay? At the end point, we cannot apply this necessary condition. What is the end point in this case? Where x is A or x is B, okay? At the boundary. Okay. Well, for example, this one, you see that this point, of course, it has minimum, but well, it's just covered by that one, right? Or even this one, right? You have a f prime x 0 equals 0, but it's not minimum or maximum, okay? Not the other way around, you see. If it is minimum, x star is minimum and maximum, of course, we need that derivative must be exist and must be 0, okay? Okay, so the next one is sufficient condition. Sufficient condition, if, well, we take the derivative, okay, until, well, you at certain order, for example, in order, you found that at derivative in order derivative at x star is not 0 anymore, then you take back one step, okay, at n minus 1 and check that n minus 1. If n is even, okay, and well, if n x star is greater than 0, then we have minimum, okay, a minimum value of fx if that is fn, okay, x star greater than 0 is positive and n is even, okay. And if n is even, again, n was it the fn, I mean n order of f, n order derivative of at x star is less than 0, that point is maximum, okay. So what about the case where n is odd? Is if n is odd, okay, that point is neither maximum nor minimum, okay. Yeah, for example, while we see this example, okay, we have 12x5 minus 45x4, right, plus 40x powered by 3 plus 5. We take derivative, okay, first order derivative, second order, third order, fourth order, and fifth order. And finally, we see that the last order where we have to stop, it's well, at fifth order. Okay, then we check the, what's it, the extreme point first. The extreme point, well, the condition for extreme point, of course, well, the first order derivative must be 0, right? So we find the point where the first order derivative is 0. We obtain that x can be 0, 1, or 2, right? And then we check at this point the highest order, that was it, the derivative, and other derivative is not 0. So for example, when x is 0, the highest, yeah, order it's third order, okay. So in this case, n is 3, right? N is 3, that means n is odd number. So when x is 0, this point is neither maximum nor minimum, okay. You can see, now you can see my screen, right? Okay, yeah. And when x is 1 and x is 2, you see that the highest order, it's what's it, second order only, because at the third order is already become 0. So the highest order is 2. So you see that it's even, right? 2 is even. So, well, what's it? Well, do you check the value? Yeah. At when x is 1, so the second order, okay, derivative, it's minus, it's negative. So well, it's a maximum point, okay. And the other case is minimum point because the second order at derivative at that point is positive. Okay, so we can see it from this graph happen. Okay, so we extend the idea of necessary condition to multivariables. Okay, so in multivariable, of course, you cannot check this, this by using this condition. Okay, so to check for the necessary condition applied for multivariable, of course you need a Jacobian first, because in the case of multivariable we have partial derivative. Okay, you know Jacobian, right? It's a kind of a gradient, okay, of a function in each direction. Okay, in x1 direction, x2 direction, or to xn. Okay, we got Jacobian, and from the the first condition, our necessary condition, of course, to guarantee the optimum point, the extreme point, the Jacobian, each element of Jacobian must be 0. Okay, that means, you can imagine that, because the derivative becomes 0, so at that point you cannot go down or you cannot go up, right? You cannot improve. I use the word improve because, it can be applied both maximize or minimize. You cannot change the objective function anymore because the derivative is 0 already. Okay, you cannot increase that objective function, or you cannot decrease that objective function anymore because the derivative already 0. Okay, you reach some point which you cannot improve or you cannot change the value. Okay, so in any direction, okay, Jacobian, because all elements of the Jacobian is 0. And what about the sufficient condition? In this case, the sufficient condition is, we have to consider Hessian. Okay, this time we use a Hessian instead. Hessian, it's a metric, of course. If you work with 2 dimension, you got the 2 by 2 matrix. But of course, if you work with 3 dimension, you will get the 3 by 3 matrix. Okay, but anyway, we check the Hessian. The Hessian at that point must be semi-definite, no, must be positive definite or negative definite. Okay, for positive definite, we can guarantee that, the point, it's that point, that x star, it's negative. Okay, no, not negative, it's minimum. Okay, but because, it's minimum because if we move out in any direction, of course, objective function will increase. Okay, so that point is minimum. So, if Hessian is negative, we can say that, that point it's maximum point. Okay, maximum point because of what? Because if you leave that x star, you are at x star, right? If you leave that x star in any direction, you see that the objective function will be smaller, right? Decrease. Okay, so if you take Hessian, you see that it must be negative for sure. Okay, so I'm not sure whether you know you understand the concept of the positive definite or negative definite or not, but it takes a long time to study whole things. We just use that concept, just positive definite or negative definite first. For that one I move to, yeah, the concept of positive definite or negative definite is defined here in this slide. A is called positive definite if we, yeah, we have x vector x, and then we times x transpose with A and x, and the final the result value, the resulted matrix, no, yeah, resulted value, it's positive. Okay, no matter x is negative, x is undefined, I mean, well, it can be mix of positive, negative, or x is positive, but if you perform x transpose ax, you will get positive. For example, this one, this A is minus 4, 0, 0, minus 8. Okay, this A, we call it negative definite because you see that no matter we what's it, we select x, any x can be 1, 1, right? Then x transpose ax become minus 12, or we choose minus 1, minus 1, then you see that x transpose ax becomes, well, negative again, becomes, it is minus 12. You see that no matter we select any x and we perform x transpose ax, we get a negative value. Okay, so what about positive definite? This is a negative definite, right? For positive definite, it works the same way, but, well, the resulted is positive. Okay, so in order to test that, you see that from the definition, it's quite apparent, it's clear from the definition. You see that you take anything x transpose ax, you got positive, x transpose ax, you got negative, right? But for testing, it's quite tedious, right? Because you have to apply in various x, yeah, and those all x must follow this expression, right? X transpose ax must be positive or negative, and you cannot guarantee that no matter how many value of x you test, but you cannot guarantee, because if you fail to satisfy this condition with any value, that one becomes, well, non-definite, right? Undefinite. So, while to test it, yeah, it's better to use the eigenvalue, because we know that for the matrix, for the positive definite matrix, the eigenvalue, all the eigenvalue must be positive. So you just find the eigenvalue. I'm not sure whether you are familiar with eigenvalue. Yeah, you learned it before, right? Eigenvalue. Okay. So, well, in this case, you see that for eigenvalue, it's very simple. For 2 dimension or 3 dimension, for the eigenvalue, we have, well, AV, right? AV equals lambda V, where V is our eigenvector and lambda is our eigenvalue. Okay, our task is, well, to find the eigenvalue, because all the eigenvalue must be positive for positive definite matrix. Okay, and in the case for negative definite matrix, all the eigenvalue must be negative. Okay, so your task is just find the eigenvalue. Okay, for the multi-dimension, well, multi-variable, I mean, yeah, for larger dimension problem, yeah, you can use MATLAB. It's easier. It's only one line of command. You got the eigenvalue. Okay. All right. So for the eigenvalue, yeah, we start from AV equals lambda V, right? Then we move lambda V to the left hand side, and then we got A minus lambda I V. Okay, becomes 0. So V cannot be 0. So A minus A subtract by lambda I must be 0. So to guarantee that A subtract with lambda I 0, determinants of this term must be 0. So we can say that the determinant of A minus lambda I, okay, must be 0. So for example, we have A as a minus 2, 3, 1, 0. So determinant of this one, it's what's it? We start from A, right? For and yeah, maybe it's difficult for you to see my slide because it's not written in the matrix, in normal matrix. Okay, we have A, which is minus 2, 3, 1, 0. Okay, it's easy for you, I think. So A minus lambda I is right, because I is what is I is identity metric. Identity, yeah, you have a diagonal as 1, right? The other is 0. Okay, so determinant of this one, you now back to our screen, our slide. Yeah, the determinant of it is lambda times the 2 plus lambda, and then minus 3 becomes 0. So well, with this one, yeah, this can be changed to lambda plus 3 times with lambda minus 1. So the eigenvalue is minus 3 and 1. Okay, so that means, well, you have 2 eigenvalues, of course, but in different direction. That means it's not positive definite nor negative definite. Okay, it's undefined. Okay, so well, what about that case when you have extreme point where the Hessian metric is not defined, it's undefined. That point we call it saddle point. Okay. Okay. So well, it's better to show you some interesting application. A moment. Yeah, I recommend you this one. It's application GeoGebra. Not sure you can see it. You can see it, right? Okay. Yeah, it's very simple for this one. Let me delete other things, and then well, you can see that you can move to see the shape of your function. But of course, we cannot plot in 4 dimension, 5 dimension is impossible, but 3 dimension is enough for us, right? For example, if you have other you see, in this direction is of course is z or our objective function, and you see the surface of our objective function. Yeah, and normally we call later I will explain you. Okay. Okay, then we move to the optimization with equality constraint. The first method is direct substitution. For direct substitution, it's easy when you have you have constraint with which is a explicit function. For example, you have, for example, let me show you this one. For example, you have this function. You have minimization of x squared plus y plus, yeah, I don't want to do sad, but xy, okay, something like this. And you have constraint in an explicit form. For example, you have y is a function of x plus 2. Y must be y equals x plus 2. You see that y is an explicit function of x, right? So this one can be rewritten as, no need to rewritten. We rewrite this objective function instead of minimize x squared plus 2y, we substitute y with x plus 2. Okay, and you will have x and x plus 2. Okay, very simple. This way you see that we can remove the equality constraint, okay, by direct substitution. Okay, and you see that we start from 2 variable, right? Our decision variable with 2, right? Original problem. And then, well, we have one constraint, okay, and you see that one constraint can remove one variable, I mean the number of variable, right? So you see that in terms of degree of freedom, what is the degree of freedom of the original problem? The degree of freedom is 1, right? We have 2 variables and we have only one condition. So degree of freedom is 1, right? For the second problem, for the reform problem, the degree of freedom also 1, right? You see that the degree of freedom reserved, but we can, what is it? We can remove, we can get rid of the, we can reduce the number of the decision variable. But the objective, the degree of freedom is still the same. Okay. Okay, so for the, what else? Yeah, it's okay. That I think I already explained that in the video about the admissible variation. Other important thing is Lagrange multiplier. For Lagrange multiplier, it's a technique for, of course, for direct substitution is very easy. But the problem is if the function, if your constraint cannot, it's your constraints are not in the form of explicit function. This is in our example is explicit function, right? But if it implicit function, you cannot do that, right? You cannot just direct substitute to get rid of the variable. So in that case, we can use Lagrange multiplier. For Lagrange multiplier, the idea is just, well, you see that for, I think it's better to explain from this program. Just one moment. So we have function of two y plus x squared plus x, and we have x square plus y square equal 1. Okay, this one. All right, so well, the first one is I show you our equality constraint first. You see that for our equality constraint, x square plus y square equal 1, you see that you can recognize this function, it's a circle, right? Yeah, and you see that because it doesn't limit the z axis. If we plot it in 3 dimensions, right, you see that we obtain a tube, something like this. Okay, it's a tube through this axis. I don't know why it's doesn't show. No. Well, it's okay. It's a, yeah, you see, it's a tube. And what about our the surface of our objective function? This is the surface of our objective function. You see that we move to this way. I'm not sure you can see my cursor. You can see my pointer, right? Okay. Yeah, if we move this way, move this way means we go up, right? That means objective function increase, right? But the x, y, that was it satisfying this one must be on this curve, must be on this curve. Okay, let me show the level curve. For example, yc, we have yc. Yeah, 5, and we have yeah, and then I move this. Okay, now you see it's better because, well, what about this plane? This plane we can call it level set or level curve. Okay, our level set is actually the, what is it, the intersect between this plane and the surface of objective function. See that all the point belong to this set, I mean the intersection of those surface and plane have equal objective function, right? Because that plane perpendicular to Z, right? All the same plane, it has the same value of objective function. Okay, but you see that it's, well, because it's a plane, but all the plane have the same objective function though, but only the point at the intersection belong to the surface, belong to the, what is it, our objective function. Okay, so if we want to minimize, that means, well, we move this plane down, right? Yeah, of course, if we can go to minus infinity, right? As long as we can move this plane down, and all the point at the intersection, okay, between the surface and plane is the set, it's our level set. Okay, because those points have the same objective function, and they belong to our objective function. Okay, so now consider the, I remove this one out first, this plane out, and now consider the constraint. What about the constraint? our constraint, actually, it is the circle, okay, on the 2 dimension. But for 3 dimension, because actually our problem, the 3 dimension, we have SAT, which is our objective function value, right? So we project our constraint as a circle back to the surface of what? To the surface of, sorry, yeah, to the surface of our objective function. So you see that while in this viewpoint, the shape of what? Of the constraint on the surface of objective function is not circle anymore. Well, need some paper. This paper, well, our objective functions look like this, right? Okay, it's 3 dimension. But if we look from the top, you see that, well, it's the constraint is circle. Yeah, but from the 3 dimension, it's not circle, because yeah, it's yeah, as we show in this graph, you see that it's not circle. Okay, we project circle, right? Circle to the surface. Of course, the surface is not a plane. If it is a plane like this, the plane perpendicular to Z, of course you project it, it's become circle. But this plane is not flat. It's not a plane like that. It's something like this. So once you project the circle back to this, it's not circle anymore. It's, well, the shape depends on the surface. Okay. So now look at this function. And I show you the plane, this one too, because our concept, if we don't have constraint, we move the plane up, we get better objective function, right? Higher. We want to maximize it, we move it, yeah, up. But once we have constraint, you see that our constraint limits the feasible region. Our feasible region is only on the, what is it? The circumference of the constraint. Okay. On the, if our objective function is a plane, feasible region is only on the circumference of the circle. Okay. But now we project it to the objective function, which is not the plane anymore. So what is it? We try to maximize it. We move the plane up to the final point where we are still in the feasible region. Okay, somewhere around here. Okay, and you see that final point, the last point, that we are still on the feasible region, and it has maximum value of objective function. Okay, we move the plane up to that point. Okay, at that point, because, well, of course, this plane, this blue plane, is just imaginary to assist you understanding what really happened. We can remove it out. But you know that, well, the maximum point is somewhere around here. You can see my cursor, right? Somewhere around here. Because of what? This point is on the circumference of the projection of the constraint to the surface. And it is the point which is on the topmost, okay, of the surface. This point has the highest value of objective function, right here. And this point has two common things. The first one is, well, the gradient of this point on the surface, on the what is it, on the surface of objective function must be equal or parallel, not equal, parallel. Yeah, gradient is equal, and the direction is parallel. Must be parallel to the what is it, gradient of the objective function of the constraint. So what we have is the gradient of that f must be parallel to the gradient of constraint, where f is our objective function and that g is our constraint. Okay, you see that this one, because it's parallel, so we need some value, we call it lambda. Okay, we rearrange this expression, we obtain gradient of objective function subtract by lambda, which is arbitrary variable, times with gradient of g must be 0. Okay, and this is the origin of Lagrange multiplier, and we call Lagrange theorem, and we call this lambda as Lagrange multiplier. This is one way to link the Lagrange method with graphical. I think this one it's easier to understand what really happened. But of course, if you prefer to prove it using mathematics, yeah, look at the slide, and also, also I explained that in my video already. We start from this one, right? The necessary condition for existence of extreme point. Yeah, and then we derive. So let me summarize. What is our Lagrange multiplier? Okay. So if we start from optimization of f, okay, f is our objective function, and we have one constraint, which is g. Okay, we can write the Lagrange function as a, L is Lagrange function. And now Lagrange function is a function of x1, x2, of course, original decision variable, and lambda is a Lagrange multiplier. Okay, and this Lagrange function is written as a combination of our objective function and lambda times with our constraint, equality constraint, only equality constraint. Okay, we deal with equality constraint first. So once we get the Lagrange function, you see that we can follow the same necessary condition where, yeah, gradient of Lagrange in respect to x1 direction must be 0. And of course, in any direction, in x2 direction also must be 0, okay? Because, yeah, we discussed that previously that the, what's it, Laplace, partial derivative in all direction must be 0, okay? And the last one you see is interesting because partial derivative of Lagrange function with in respect to Lagrange multiplier, we obtain the constraint, okay? So the constraint must be 0, okay, to guarantee the feasibility, okay? So we don't have that one, just one moment. Try to show you the example. Now look at the example. We have minimization of minus 3x squared minus 10y squared. Okay, and we have only one constraint, which is x squared plus y squared minus 1 equals 0. Okay, so for Lagrange function, our Lagrange function is a combination, right, of objective function, this one, okay, and lambda times with this constraint, okay. For this one, you see, in front of lambda, you can put plus or minus. It depends. Yeah, it depends on you. Because if you put plus here, plus lambda here, all right, once you solve it, it can be minus, right? Or if you put minus there, if while the original one is minus, it will become plus. Nothing wrong. You can write plus lambda g or minus lambda g. It's okay for both. So the condition, we find the derivative of our Lagrange function in x component, in y components, and in lambda component. Okay, we obtain different expression, and all these expression must be 0. Okay, and from these equations, you solve the algebraic, okay, equation and obtain x, y, and yeah, lambda also. At the same time, you get lambda. Okay, and for this equation, you obtain how many points? 4 points. Okay, from this system, you got 4 points. Okay, where x, y 0, 1, 0, minus 1, 1, 0, minus 1, 0. Okay, you can solve it, right? From the first one, you see that minus 6x minus 2 lambda x, you can move the common, yeah, x out, and then you can guarantee that x must be 0 or the rest term. I mean, well, 6 minus 6 minus 2 lambda becomes 0, something like that. Okay, then you can find lambda. Okay, at that point, and then you can find the y. Okay, so this is the, well, the shape of the objective function, and also what's it, the constraint. Okay, and you see that this tube, this pink tube, is our constraint. Okay, because our constraint is, well, x squared plus y squared minus 1 becomes 0. That means it's a circle, right? Project the tube, project the circle to the surface. Okay, the same idea. What about this one? X minimize x squared. This one is not. Sorry, I skip this one first. Move to this one. Minimize half of, what is it, x squared plus y squared. Can you write down the Lagrange function. What is a Lagrange function? Oh, the Lagrange function is okay. 1 second. Y square. I use plus lambda. Okay. And the condition, what about the condition? The first condition is, well, respect to x, it's become 2 x, then it becomes x plus lambda 0. Okay. And in y component, y plus, no, minus. Okay. And the last one is easier. Okay. So you can solve for x, y, and lambda. Okay. As I told you that, well, this point, the point we obtain, the points we obtain are extreme point only. Only the candidate. We don't know whether these points are minimum, maximum, or certain point. Okay. It can be minimum, it can be maximum, it can be certain point. You have to test it. And how we can test it? We test it using Hessian. Okay. Hessian of the objective function at that point. Okay. If it is positive definite matrix, it's minimum point. If it is negative definite matrix, then it's the maximum point. If it's undefined, undefinite, that point must be certain point. Okay. Okay. So we use Lagrange multiplier, but the result is, of course, it's only the candidate. Yeah, the extreme point. Okay. Now, what happens if we have multiple constraints? For example, we have minimize fx. I can say fx only. X can be vector. Okay, and we have g1 x equals 0, g2 x equals 0, and so on. The Lagrange function in this case becomes fx plus lambda 1, which is respect to g1, plus lambda 2, g2, lambda 3, g3 x, and so on. Okay. Okay. Well, if you watch the video, I mentioned I introduce you the Courage-Kuhn-Tucker also. For Lagrange method, we use Lagrange method to deal with equality constraint. But in case we have inequality constraint, we cannot use Lagrange method. Later, well, another method developed by, of course, it's based on the Lagrange method, but developed by others. Three mathematicians, I think, Courage-Kuhn-Tucker, we call it KKT. And for KKT, Courage-Kuhn-Tucker, of course, we use that KKT to deal with the inequality constraint. For inequality constraint, what is the difficult point of inequality constraint? I will show you. Okay. For example, this one, we have objective function of x squared plus y squared. And we have inequality constraint of x plus y minus 1 must be greater or equal 0. 2 minus y must be greater or equal 0. And y squared minus x must be greater or equal 0. Okay. In case of equality constraint, you know that x, if this is equality constraint, for example, x plus y minus 1 must be 0. It's okay. All the points that satisfy this equation, right? But for inequality constraint, you see that our what's it? X and Y, our candidate can be greater than 0, just only greater than 0. It's not equal, that one. So you have an open area, right? Instead of the line on the surface. But you have open area, open volume. So it's more difficult than in the case of equality constraint, because equality constraint, you know that all these variables must satisfy this constraint, this equality constraint. Okay. So the point is, of course, you can assume that this because you don't know whether this constraint is active or not. The constraint active means, well, this constraint becomes equal. Okay, instead of greater than equal, it becomes equal. Okay, it belongs to that line or that surface or that plane. Okay, for example, the second one, 2 minus y must be greater or equal 0. You don't know whether y is 2 or not. But of course, y cannot be greater than 2, right? From the second constraint, 2 minus y is positive, right? This constraint. Okay, y can be 0, y can be negative, y can be anything down from 2. But the easiest one, of course, when y is 2, you know, y is 2, it's easy to solve. But you don't know whether it's active or not. Okay, you got the point? So for KKT condition, it has condition like this. Yeah. I will write down from this example. You have function, right? Minimize x squared plus y squared. And we have constraint of x plus y minus 1 is 0. Okay, so for Lagrange, of course, we use the same Lagrange function as I will use lambda. Actually, it can be any other variable. But if we write this way, that means we force everything. I mean, every constraint to be active, right? But it's not true because we don't know actually it's active or not, right? So what you need is, yeah, you need a condition where lambda times, for example, lambda 1 times x plus y minus 1 becomes 0. Why? Why do we need this condition instead? For equality constraint. Because if these constraints satisfy, this constraint, yeah, x plus y minus 1 becomes 0. So you don't care about y lambda 1 anymore because it's already 0. Okay. However, if x plus y minus 1 is positive, is not active, you force it to be 0, then that means lambda 1 must be 0. Okay. So you need lambda 2 and lambda 3. No. This one must be 0 too. Okay. Okay. So this is a trick. So when you formulate the condition, for example, of course you need this yeah, this x becomes 0, right? This y becomes 0, but you don't need other condition. I mean, well, what is it? That one. Partial derivative, gradient of L, gradient of Lagrange function respect to lambda. You don't need that one because it's already covered by this one, right? And also you don't need the gradient of L in lambda 2 direction because it's already covered by this. And this one too. Okay. What about the case where we have both equality and inequality constraint? If we have both equality and inequality constraint, of course, we treat the equality constraint first using Lagrange method. Okay, and you add another condition for inequality constraint. Yeah, derived from KKT. Okay, and this condition is we call KKT. Yeah, Courage-Kuhn-Tucker condition. If we know the extreme point, of course we test it. If those extreme points satisfy with this KKT condition, yeah, if any point satisfy that KKT condition, we can call it, yeah, it's an extreme point. Okay, you can solve this one by yourself, this example. This one. Oh, we solved that already. This one, you can solve this one by yourself. And also this one. You can try solving this one. Okay, any questions from the oh, okay. Yes. One moment, I turn this off.
I think for more understanding, could you please solve for one example to the finish?
Okay, yeah. Which one? Which one? Which one is good? Yeah, this one is good. Just one moment. Okay. Yeah, we can do this one, and you have to help. Just one moment. I try to look for some. X square plus y square, right? And what we have x. Okay, this one is good. So KKT condition ในหน้าจอเป็นอะไรอยู่ฮะเป็นสไลด์หรือเป็นอะไรอยู่โอเคเป็น iPad นะโอเค so the KKT condition we have 2x minus lambda 1 minus lambda 3 becomes 0. Is it correct? Respect to 1, x1. Okay. And the next one is 2y minus lambda 1 plus this y lambda 2, yeah. And minus 2y lambda 3. Is correct?
No, I think lambda one is a plus minus one. Plus lambda
2y
one.
lambda 3, no? Lambda 3. Lambda 3, we have lambda 3. Lambda 3 is y2 minus x, right? So we lambda 3 to y 3 to y.
It should be plus, not minus.
Oh, it depends. Well, you can
Okay.
yeah, plus or minus the same. Minus, plus, minus. Okay. And what else do we have? We need, because all of these are, what's it? Inequality, right? So So we need that lambda 1 x plus y minus 1 becomes 0. Lambda 2 minus y becomes 0. And lambda 3 here, y square minus x becomes 0, right? So I leave you to solve it. Yes. X and y, lambda 1, lambda 2, lambda 3. Okay. We can start from this one first. Well, lambda 1 times with x plus y minus 1. You see that if lambda 1, of course, lambda 1 can be 0, right? In the case, the first case, lambda 1 is 0. Yeah, this is correct. Or the case, for example, lambda 2 is 0. Lambda 2 can be 0. So 2 minus y doesn't need to be 0. Or the case where y is 2. Okay. Yeah, something like that. Then find the, it look well as if not difficult, but it's tedious. Yeah, because you have 5 variables already. We have condition that the condition that well satisfy on the KKT, it's one, yeah, this one, this condition. Oh, sorry. And other points is conjugate with of this one is 3. Okay. so wow any question สุภวัฒน์มีคำถามไหมครับ
ไม่ครับ
โอเคฮะเข้าใจนะฮะ What about you Kadim any question
No, I can.
okay thanks Asan
No, sir, no question.
okay no question okay good well you can study more on the what is it Lagrange method and KKT okay and then well there are a lot of a bunch of video explain the KKT and Lagrange in YouTube yeah if you search through Lagrange method and KKT method Courage-Kuhn-Tucker method well you can find other ways of explanation of Lagrange method and also KKT all right also take some time to practice okay to solve it because of course KKT or Lagrange method give you the conditions but in order to find the solution you have to solve algebraic yeah equation okay what about you Sasmita you can follow the content
yes
okay good well next week what is next week 21st I'm not here well I will be in France next week so I will prepare a video for linear programming for you and then well on of course at the same time 9:30 I will be online and send you the link we can meet over Zoom okay in case you have any question then we can discuss okay for today I think it's enough no more question right no more question we close today class